Today I am going to discuss about how to find the eigenvalues and eigen vector for a matrix. Okay, so for that I'll take a 3 cross 3 matrix as an example. So let A be our matrix, and it's a 3 cross 3 matrix, and it is given by -2, -4, 2, -2, 1, 2, and 4, 2, and 5. So this is a 3 cross 3 matrix, right? So what we are going to do is we are going to find the eigenvalues and eigenvector for this matrix. Okay, so it's a 3 cross 3 matrix. So in order to find the eigenvalue, we have to write the characteristic equation. Okay, so the characteristic equation or characteristic polynomial is also called polynomial. Okay, so we have to find this characteristic polynomial, and it is nothing but it's the determinant of a minus lambda I. Okay, and we have to equate it equal to 0. Okay, so what is lambda I? So here lambda is the eigenvalue we are going to find. So we have to find the determinant of a minus lambda I and equate it to 0. By that way we can form the characteristic equation, and by solving the characteristic equation we get the values of lambda, where lambda is the eigenvalue. Okay, so for a 3 cross 3 matrix we have 3 eigenvalues. For a 3 cross 3 matrix we have 3 eigenvalues. So for 2 cross 2 we have 2 eigenvalues, and for 4 cross 4 we have 4 eigenvalues. Okay, for n cross n matrix we have n eigenvalues, right? So let's form the characteristic equation. So it's a minus lambda I, and our a is given by, so this is our a. So a equals to -2, -4, 2, -2, 1, 2, 4, 2, and 5. Okay, and this lambda I is nothing but, so it's so I is unity matrix, which is 1 on the diagonal elements. Okay, 1, 1, 1, and the remaining elements are 0. Okay, and if we multiply by this identity matrix, so this is I. So if we multiply by lambda, we have lambda at the diagonal elements, right? And we have to find the determinant. Okay, so this is this is a, and this is lambda I, and we have to find the determinant. So we have determinant of -2 minus lambda, and this is -4 minus 0 is -4, 2 minus 0 is 2, and similarly for the other terms we have 1 minus lambda and 0, 4, 2, 5 minus lambda. Okay, so now we also equate this determinant to 0. Okay, so if we want to find the determinant, what we have to do? So the determinant is given by -2 minus lambda times this element into this element, right? Sorry, this is not 0, this is 2. We have 2 here. Okay, so this is 2. So we have 1 minus lambda times 5 minus lambda minus 2 into 2 is 4, right? And we have minus of minus 4 is plus 4 times, so we have to leave this column and this row. So we have minus 2 times 5 minus lambda minus 2 into 4, which is 8, right? And finally we have plus 2 times this 2. We have to skip this column and this row. So we have 2 minus 2 into 2 is minus 4 times 1 minus lambda, be equal to 0. Okay, upon expansion, we have minus lambda cube plus 4 lambda square plus 27 lambda minus 90 equal to 0. So upon expansion and simplification, we end up with this equation. Let me multiply by this equation by minus 1 on both sides. So we have lambda cube minus 4 lambda square plus minus 27, right? Minus 27 lambda plus 90 equals to 0. So we have to find the root of this equation. The root of this equation gives the eigenvalue, right? So this lambda are the eigenvalues. So the root of this equation gives the eigenvalue. So in order to find the root, let's try to factor out lambda minus a term such that this equation reduces to quadratic form. Okay, for that we have to do what's called our long division. So in order to perform the long division, we have to collect the coefficients of the above equation. So the coefficient of lambda cube is 1 and the coefficient of lambda square is minus 4, the coefficient of lambda is minus 27, and the lambda power 0 term is 90, right? So we have to do the long division. Okay, so next we have to do long division. So the trick to find the value such that we have to do long division. So let me explain how to do it. Okay, so let's try to find a divisor which divides this last term, and that divisor should be chosen from the prime numbers. So the list of prime numbers we have are 1, 3, 5, 7, 11, etc. right? So we can choose 1 or 3 or 5 or 7 or anything, but the only condition is these numbers we choose, no, it should divide this which is a divisor of this one. Okay, so we know 1 will divide 90, 3 will divide 90, 5 will divide 90, but 7, 11, etc. won't divide. Okay, so let's try to use this one. Okay, so we have to choose, we have to substitute this value in the above equation such that this equation reduces to 0, which is on the right hand side. Okay, let's try to check whether which number divides this solves this equation. Okay, sorry, excuse me. So for lambda, let me choose lambda equals to 1. Okay, the first choice, first guess. Okay, so if we substitute this one, what we have is 1 cube minus 4 minus 27 plus 90. which is obviously not equals to 0. Okay, so the next thing we can choose is 3. Okay, so for lambda equals to 3, if we substitute this in this equation, we have lambda cube, which is 3 cube, so 3 cube is 27, right, minus 4 into 3 square. 3 square is 9, 4 into 3 is 36, so minus 36, minus 27 into 3, which is minus 81, plus 90 equals to 0. Okay, so we have to check whether it is equal to 0. Okay, so we have 90 here. If we add this to 27, we have 117, so we have plus 117, and we add this to, we have 6 plus 1 is 7, and 3 plus 8 is 11, right? So we have minus 117, so this equals to 0. So we can use 3 as our initial our guess. Okay, so if we put 3 here, and if we try to divide this, so we have, so this 1 is not cannot be divided by 3, so we have to simply bring it down. So 1 into 3 is 3, right? So we have to add these two terms. If we add, we have minus 1, so minus 1 into 3 is minus 3, so minus 3, and minus 27 is minus 30, and if we multiply by these two, we have minus 90. Okay, so perfectly ends with a 0 remainder. So our one of our eigenvalue is lambda equals to 3, this one. Okay, and the remaining eigenvalue, let me rewrite the above equation. So the above equation, this equation, right, this lambda cube minus 4 lambda square minus 27 lambda plus 90 can be written as lambda minus 3, this 3, right, into, so this is the coefficients of the quadratic equation. So the power of lambda square is 1, and the power of lambda is minus 1, and the constant term is 30. Okay, so this is equals to 0. So this is not, this equation is nothing, this equation and this equation are same. What we did is we just factor out this lambda minus 3 by this technique. Okay, next we have to find the root of this quadratic equation. Okay, so this quadratic equation, so this is the product term, so this is our product term. So and the sign finding authority is this coefficient. Okay, minus sign. Okay, so what are the factors of 30? So we can get 30 by multiplying 1 and 30, or 2 and 15, or what else, 3 and 10. So it is not a factor of 4. We have 5 and 6, right? So let's try to find. Okay, so this product, and if we have sum it, it won't equals to 1, so this one is not possible, and this gives the product, and we can by no way we can sum this to 1, so this is not, this is also not possible. Similarly, this is also not possible, but this one is possible, right? Because 6 into 5 gives 30. Okay, and we can put the sign deciding authority, this sign to the greatest value. So if we sum up this one, we can have minus 1, right? So our, let me put this in this way, this here. Okay, So what's our factor? So we have lambda minus 3, right? And we have lambda plus 5 into lambda minus 3, lambda minus 6, right, equals to 0. So if we multiply this, we will get this equation. If we multiply by this equation, and if we multiply this equation, this all terms, we end up this to this equation. So what we did is we just find the roots. Okay, so these roots are nothing but the eigenvalues. So what are the eigenvalues? Let me put the subscript to distinguish the roots. So lambda 1 equals to 3, which comes from lambda minus 3 equal to 0. Therefore lambda equal to 3, which is one eigenvalue. And another eigenvalues is lambda 2 is lambda plus 5 equals to 0, or lambda equals to minus 5. It's the next eigenvalue, and the third eigenvalue is nothing but 6. Okay, so these are the eigenvalues. Okay, eigenvalues of the equation of the matrix A, right? So with this, let me move on to the eigenvectors. So in order to find the eigenvectors, so let's try to find the eigenvectors. Next thing is find the eigenvectors. Okay, in order to find the eigenvectors, what we have to do is we have to substitute this eigenvalues in the equation a minus lambda I, okay, equals to 0. So these are matrices, right? And try to solve the vector. So what we have to do is we have to substitute this eigenvalue in this equation and to find the x. Okay, so this x is the eigenvalue. This is the eigenvector. Okay, so this is the eigenvector. So let me work out one of this thing so you can understand. So for a minus lambda I, for let me choose lambda equal to lambda 1 here. Okay, so what we have is for lambda equals to 3. Okay, the first eigenvalue, this is the first eigenvalue. We have a minus lambda I is nothing but minus 2 minus 3, okay, and minus 4 2 and minus 2 1 minus 3. So this is the eigenvalue, and this is 2 and 4 2 and 5 minus 3. Okay, so this is a minus lambda I, and instead of x we have 3 vectors, x1 x2 x3, right? And we have the null vector space, so we have 0 0 0. Okay, this is what I simply in a compact form I written it in this way. Okay, so let's try to solve this this matrix equation. So what we have is, if we simplify this, we have minus 5, right? Minus 5 minus 4 2 minus 2 minus 2, right? And 2, and this one becomes 4 2 and 2. Okay, and this x1 x2 x3, okay, equals to 0 vector. If we perform the matrix multiplication, So we have minus 5x1 minus 4x2, right, plus 2x3 equals to 0. Okay, so this way equals to this one. Okay, this term. Similarly this and this. Okay, so we have minus 2x1 minus 2x2 plus 2x3 equals to 0. Okay, and the third one is 4x1 2x2 plus 2x2 plus 2x3 equals to 0. Okay, so this is equation 1a, 1b and 1c. Okay, so we can solve this by choosing some values for either for x1, x2 or x3. Okay, so let us choose x1 equals to 1 here. Okay, and we can take either any of these two equation. So let's put x1 equal to 1 in equation 1a and 1b. Okay, and subtract them. Okay, let's put x1 equal to 1 in 1a and subtract it in from 1b. Okay, so if we put x1 equal to 1 in this 1a and 1b and subtract, what we have is minus 5, right, minus 4x2 plus 2x3 equals to 0, and minus 2x2 plus 2x3 equals to 0. Okay, and the next thing is we have to subtract this one. So if we subtract, this term becomes 0, get cancel out, and what we finally have is, so this is minus this is minus 3, so this becomes plus, right, minus of minus, this becomes plus, plus 2 minus 5 is minus 3. Let me change this one, this may confuse. Okay, so this becomes positive and this also becomes positive and this one becomes negative, right? So plus 2 minus 5 is minus 3 and plus 2 and minus 4 is minus 2x2, right, equals to 0. Okay, or minus 2x2 equals to 3, or x2 equals to minus 3 by 2, right? So we have x1 here, x2 here. We can substitute this x2 in x1 and x2 in any of the above equation and solve for x3. Okay, let me put this value of x1 and x2 in equation 1c. Okay, so substituting value of x1 and x2 in 1c, we have you can substitute in any equation, but for let me choose 1c. Okay, so it's 4 into x1, therefore it's 4. So 4, this 2 into x2 is minus 2 into minus 3 by 2, which is minus 3, right, and we have this 2x3, right, plus 2x3 equals to 0. Okay, and this is 1, right, 4 minus 3 is 1 plus 2x3 equals to 0, or x3 equals to minus 1 by 2, right? So our eigenvalue for the the eigenvector for the eigenvalue. So the eigenvector for the eigenvalue lambda equals to 3 is nothing but this vector x1, x2 and x3. So x1 is 1, right? X2 is x1, x2 and x3, right? So x1 is 1, x2 is minus 3 by 2 and x3 is minus 1 by 2, right? So this is the eigenvector for the eigenvalue lambda equals to 3. Similarly, you have to find the eigenvector for the eigenvalues lambda equals to minus 5, this one, and lambda equals to 6. Okay. Before doing that, you also have to find the norm of this vector. Okay. So norm of this vector is nothing but the magnitude of this vector. So the norm, okay, so norm equals to root of, it's nothing but root of, how we find the magnitude, we have to square each of this term and sum it, and we have to take the root. Okay, so 1 square plus minus 3 by 2 the whole square plus minus 1 by 2 the whole square. So the norm is root of 1 plus, so this is 9 by 4, right? And this is 1 by 4. We have 10 by 4, 10 by 4, and this is equals to root of 14 by 4, or we can take this 4 outside, so we have root of 14 by 2, right? So this is our norm. Okay, this is our norm, and we have to use this norm to normalize this vector. Okay, in order to normalize this vector, we have to divide each of this element by the norm. Okay, this n. Okay, so we have, so the normalized eigen vector for lambda equals to 3 is 1 divided by the norm. Okay, so this is root of 14, and we have a 2 here, we can take this 2 to the numerator, right? So we have 2 by root 14, and the next term is minus 3 by 2, right? So it's minus 3 by root 14. We have a 2 here and a 2 here, so they get cancelled, and finally we have minus 1 by 2, which is 1 by root 14, right? So this is normalized eigen vector. Okay, similarly you have to find the eigenvectors for lambda equals to minus 5 and lambda equals to 6. Okay, you try to solve it by yourself, and the answer should be the normalized one, right? The normalized one for lambda equals to minus 5, I got x1, I choose x1 equals to 1, so I got x2 equals to 1 by 2 and x3 equals to minus 1 by 2. This is for the case of lambda equals to minus 5. Okay. Similarly, for lambda equals to 6. So similarly for lambda equals to 6. For lambda equal to 6, I choose x1 equals to, here also I choose x1 equals to 1. So I got x2 equals to 6 and x3 equals to 16, right? And the normalized and the normalization factor is for this vector is n equals to root 3 by 2. Therefore the normalized vector, so the normalized vector x1 equals to root 2 by 3, x2 equals to 1 by root 6 and x3 equals to minus 1 by root 6. Similarly, here I got the norm as root of 293, I think so. Yeah, it's 293, and the normalized vector or x1 equals to 1 by root 293, x2 equals to 6 by root 293 and x3 equals to 6 by root 293. Okay, so these are the normalized eigenvectors for the eigenvalues lambda equal to minus 5 and lambda equals to 6, right? So finally we also have to discuss about the diagonalization vector. Okay, sorry, the diagonalization matrix, matrix D, right? So this diagonal matrix is nothing but D equals to the lambda 1, lambda 2, lambda 3 and 0. Okay, so this is a simple thing. So this is the diagonal matrix. For our case, the diagonal matrix of A is D equals to, what are the eigenvalues? We have 3, minus 5 and 6, right? So for our case, this is our diagonal matrix. Okay, this is the diagonal matrix. We also have to find another matrix called the P matrix, which is nothing but the matrix of the eigenvectors, right? So here the order is very important. So our D matrix is nothing but 3 0 0 0 minus 5 0 and 0 0 6, right? And the P matrix, okay, P matrix is nothing but the eigenvector matrix. Okay, so the eigenvector matrix of this eigenvalue 3 is, what's the eigenvalue? And we have to choose the the normalized eigenvalue. So in our case we have, for 3 we have 1 by root 14, right, minus 3 by root 14 and minus 1 by root 14, right? This corresponds to this 3, okay? And for 5 we have the normalized as root 2 by 3, 1 by root 6 and minus 1 by root 6, okay? And for the eigenvalue 6 we have one by root 293, 6 by root 293 and 16 by root 293. So this is the P matrix. So another thing to do is in all the case this P inverse A P equals to D, okay? If we take the inverse of this P matrix and matrix multiply with A and then matrix multiply by P, we will end up with this D matrix, okay? So this is called the similarity transformation. Similarity transformation. This is a similarity transformation, okay? So the topic is we have to find the eigenvalues by forming the characteristic equation, and for finding the roots, thereby we get the eigenvalues, and using the eigenvalues in the characteristic matrix we can find the eigenvectors, and for each eigenvectors we can form this P matrix, okay? And the diagonalization matrix is nothing but the eigenvalues on the diagonal elements, right? So with this we complete the eigenvalue problem, the eigenvectors, diagonalization matrix and similarity transformation, okay? So try to solve some other problems, and with this we have completed that eigenvalue problem and the similarity transformation in our syllabus, right? Okay, thank you.